Hello and welcome. This is Mouse Gunner, and we're back with part 2 of my video series covering how revolvers work. As the first video focused only on examples made by Colt, in this video we're going to take a look at some alternate brands and more unusual methods of operation found in revolvers. To start things off, we're going to take a look at an example made by Smith & Wesson, not only as a reminder of the basic principles of revolver operation, but also to go over what differences there are between the historical rivalry of the Colt and Smith & Wesson brands. So, as we have done before, let's first identify the three main parts of revolver operation found on this example. The first part is the cylinder, which contains a number of cavities known as chambers that hold the ammunition or cartridges. At the back of the cylinder is the ratchet teeth, which, just like with the Colt Python on my previous video, this is a swing-out cylinder style revolver. So the ratchet teeth are not actually directly attached to the cylinder. Instead, they're attached to the extractor star, which you may just be able to make out here. And we'll see that in more detail when we go through the reloading process. The cylinder also has a number of these locking notches cut into the cylinder that the cylinder stop, which is our next part, interacts with. The cylinder stop goes up into those locking notches, locking the cylinder in place to keep it in line with the barrel. And the importance of that I discuss in my previous video. The last part is the hand, which is actually on the opposite side of the revolver than what we've seen with our previous examples of Colts. And we'll explain why that is the case and what effect that has as we go through the operation of the revolver. Now, just like the Colt Python, the hand is directly attached to the trigger. So as we cock the hammer, again, similar to the way the Colt Python worked, the hammer is going to hook onto the end of the trigger. And as the trigger gets pulled upwards, this end, it's going to pivot upwards and drive the hand up along with it. And as the hand gets driven up, it's going to interact with one of the ratchet teeth. And because the cylinder is fixed along a central axis point, as the ratchet tooth gets pushed up, it's going to rotate along that axis point until the hand has cleared the ratchet tooth, and then the rotation ends. The cylinder stop is also going to interact with the trigger, unlike the Colt Python, where we had this more complex lever mechanism that would act upon the cylinder stop. Now it's just the trigger directly acting upon the cylinder stop. So as the trigger pivots, it's going to pivot downwards on this end because of its axis point here. And as it pivots downward, it's going to pull downward on this end of the cylinder stop, which pivots in turn, compressing the cylinder stop spring here. And then eventually, this finger here on the trigger is going to go past its contact point with the cylinder stop, and the cylinder stop will break free, and the spring will drive the cylinder stop up. But because the notch is not yet in line, the cylinder stop is just going to drag along the outside of the cylinder, which is why we have this groove kind of worn into the side of the cylinder. Eventually, it's going to come down into the locking notch, locking the cylinder in place so that the cylinder will not lose its alignment, or the chamber will not lose its alignment with the barrel. Now, if you saw my previous video where I covered Colts, you might have noticed a difference between this example and those Colt examples when we saw the rotation of the cylinder. The cylinder actually rotates in the opposite direction as it did with the Colts. With the Colts, with the hand being on the left side of the revolver, as it was being driven upwards, it would push on the ratchet tooth in the opposite direction, making it rotate clockwise. Well, with the Smith & Wesson, because the hand is on the right side of the revolver, the hand is driving the ratchet tooth upwards in a counterclockwise direction. So that is one difference of Colts and Smith & Wessons. Colts tend to rotate clockwise. Smith & Wessons, at least modern ones, tend to rotate counterclockwise. And that really doesn't have any direct effect on the function of the revolver outside of that rotation. It doesn't really impact the overall function of the revolver all that much. It's just a quirk of Smith & Wesson design versus Colt design, and other brands will take one direction of rotation or the other depending on their brand identity. And usually speaking, if you see the revolver rotate one way or the other, you can deduce what side the hand is on. So if the cylinder rotates counterclockwise, then the hand is going to be on the right side of the revolver. If it rotates clockwise, then it will be on the left side of the revolver, as we saw with all of our Colt examples. Let's now take a look at the reset of the hand and the cylinder stop as the trigger is pulled and then released. So with the trigger pulled in fully, the hammer will drop forward. And because the trigger is being pulled in slightly, it will pivot some, so the hand will be driven up slightly upwards. But because the hand and the cylinder stop are not actually directly being acted upon by the hammer, as it comes forward, nothing really will happen there. It's not until the trigger is released that the hand starts to come back down. It's going to contact the back of this ratchet tooth here, skip along it, right along the outside of the ratchet tooth, and once it goes past it, it will be driven back down underneath the ratchet tooth, so that when we were to pull the trigger again in double action mode or cock the hammer if we wanted to fire in single action mode, the hand would come back up and act upon the ratchet tooth as we've seen before. Now what causes it to be driven back forward is actually a spring within the trigger here. So you see this spring here. So as the hand comes back down, this spring within the trigger is acting upon this pin. So this is the pin that is the axis point of the hand. This is where the hand pivots along with the trigger. This other pin is what's acted upon by the spring. So as the hand comes down and contacts the ratchet tooth, because it gets pushed back a little bit, this spring is going to get compressed. But once the ratchet tooth is beyond the ratchet tooth and starting to be driven inward, this spring will push down on the hand to make sure that it pivots in underneath that ratchet tooth. So that's how that works. And if we come back out, we can see the interaction with the trigger and the cylinder stop. So as the trigger comes back forward, being pushed in by its return spring, the finger here is going to contact this surface on the cylinder stop, which is going to push it inward because of the cut of the hole that the pin that attaches the cylinder stop to the frame rides along. And it's going to ride along this elliptical shaped hole, allowing the cylinder stop to be pushed inward, compressing the cylinder stop spring. And once the finger on the trigger goes beyond its contact here along the slope of the cylinder stop, the cylinder stop is free to then get pushed back in by its spring. And now the finger is on top of the cylinder stop, so that when we were to pull the trigger in double action mode or cock the hammer again, that this finger would act upon the cylinder stop. So that inward push is just a simple way of allowing the trigger to come along and get back on top of the cylinder stop. And finally, let's take a look at the reloading process for this model of Smith & Wesson. And this is going to be pretty similar to what we saw with the Colt Python. The main real difference is the cylinder release latch and how the cylinder itself is released. So with the Colt Python, the cylinder release latch was pulled back on, and it was the cylinder release itself that held the cylinder in the frame. With a Smith & Wesson, it's actually this spring-loaded pin that comes into this cutout that you might be able to see here in the frame that holds the cylinder in place. And the cylinder release latch is actually pushed forward rather than pulled backwards. And when it is pushed forward, it presses in on that spring-loaded pin. And once that pin is pushed in, the cylinder is no longer being held within this hole within the frame, so we can push back out on it and swing it out along its crane arm. Then you press on the ejector rod, just like what we saw with the Colt Python. This pushes out the extractor star, which, as I discussed earlier, is where the ratchet teeth are attached rather than the cylinder itself, with some of those early examples of Colts. And then the spent cartridges are pushed out, and we insert new cartridges, then we can push the cylinder back in. Now, as the cylinder is getting pushed back in, it's going to meet this sloped surface on the frame here. And when it meets that surface, the pin is going to get pushed back in. And when that pin comes back to where the hole is, its compressed spring will push back on the cylinder release and drive it back. It has enough force to overcome the spring within the cylinder release mechanism, driving it backwards. The next example we're going to take a look at is the Webley revolver, which is an example of a top brake revolver design. And just like before with our other examples, I'm going to start off by identifying the three main components. The cylinder, which has ratchet teeth attached to a star extractor at the back of the cylinder, and locking notches cut into the sides of the cylinder, which interact with the cylinder stop here. And the last part is the hand, which is directly attached to the trigger. And just like the Smith & Wesson and Colt Python models before it, the main reason that the hand is attached to the trigger rather than the hammer is because this is a double action capable revolver. As the hammer is cocked backwards, just as we've seen with the other two double action examples we've seen so far, the hammer is going to hook onto the back of the trigger here and pull the trigger upwards, pivoting the trigger back. And as this part of the trigger pivots upwards, it's going to bring the hand along with it because of the attachment point of the hand to the trigger. So as the hand is forced upwards, it's going to push up on the ratchet tooth above it, rotating the cylinder around just as we've seen before until the next chamber is in line with the barrel. Now on the reverse side, the cylinder stop has to lock the cylinder in place to keep that chamber aligned with the barrel. And it does this by being within the trigger and being held down by this flat spring here. So as the trigger pivots, so too does the cylinder stop, because the flat spring here forces it to go along with the trigger. But eventually, it hits a point in the frame where it can no longer go any further down. And at that point, the flat spring here forcing down on it doesn't stop it from rotating the other way. And as it rotates the other way, the flat spring slides along this sloped surface on the cylinder stop and eventually snaps around to this notch. And when it snaps on this notch, it's going to force, through the release of its spring tension, the cylinder stop back up and into the locking notch, locking the cylinder in place and keeping the chamber aligned with the barrel. For the reset of the hand and the cylinder stop after the trigger has been pulled and the hammer has fallen, as we've seen before, the hammer falling doesn't really act upon the hand or the cylinder stop because they are tied to the trigger. So it's not until the trigger is released and starts to pivot back down that the hand is brought downward. And the reason that the trigger comes back forward and the hand comes down is the interaction of this lever here, somewhat similar to what we saw on the Colt Python. So this spring here is going to force down on the lever, and that lever is in between the trigger and the hand. So as that lever pushes down on the trigger and the trigger and hand come downward. Now, the animation here, the timing is very poor, as this lever doesn't move until we see significant movement with the trigger. But in reality, the lever would have moved at the same time along with the trigger and the hand. And how it would have interacted is it would have pushed down on this part of the hand, and it would have also kept the hand in alignment. So as the hand comes down, it's going to slide along the ratchet tooth, and it's this lever that is going to help bring the hand back underneath the ratchet tooth by pushing down and making sure that it pivots forward just through the slope shape of the lever itself. Again, similar to the way that the Colt Python worked. And again, you are going to have to forgive the animation and its poor timing in that regard, and just imagine that that lever moved along with the trigger and the hand. For the return of the cylinder stop, as the trigger is released and the lever forces the trigger to pivot back around, the cylinder stop is not going to move. It's pretty much going to stay in its current position because as it's being pushed down by the flat spring here, it can't really go any further up because it's already in the locking notch. As a downward push here would actually cause this end to pivot. So it's going to be held up by the flat spring here, but eventually the flat spring is going to continue to bend until it slides off this notch here. And then when it does so, it's going to snap back down. As a matter of fact, you can see the poor timing of the lever here as this part of the hand actually phases through the lever, showing you that that lever would clearly not be there at this time. In any case, as the trigger comes back forward, then the flat spring will come back into this notch so that when the trigger is pulled again or the hammer is cocked and the trigger pivots, the flat spring can act upon it again. Now, top brake revolvers are somewhat of an unusual sight today, being more popular in the late 19th and early 20th centuries, and we'll discuss why that is a little bit later in the video. But it's the reloading process of top brake revolvers that really set them apart from the other examples we've seen so far. To reload a top brake revolver, you have to first open the latch, usually found at the top of the frame, and in this case, it's found here. And to do so on the Webley revolver, you first push down on this lever on the other end of the latch so it pivots out of the way, as we see here. And once it pivots free of the frame, the user can then pull down on the barrel, opening the action. And as the action opens, the extractor star automatically comes out, extracting the spent cartridge cases, and then automatically comes back down so that the user can reload fresh cartridges. And then the user pulls up on the barrel, bringing the frame back down. Now, the animation here shows the latch being operated by the user to bring it out of the way. You could just allow the frame to contact it, and due to this rounded surface, it would just push back on the latch until it got firmly in place within this lug here, and then the latch would just automatically snap back in place due to its return spring. But you could also activate the lever here to bring the latch back if you desired, like what we see in the animation. In principle, this is a simple design. The latch is activated, this compresses a flat spring here, and then once the user stops activating the latch, the spring brings the latch back into its former position. The frame pivots along its hinge point here, open up the frame, go through the reloading process, close back the frame, the latch gets forced out of the way, compresses the spring, and then the spring brings the latch back in place again. What makes this complicated is the automatic ejector, and it's that we're going to focus most of our attention on. The ejector rod itself works pretty much exactly the same way as the other ejector rods we've seen before. Pushing in on this forces the extractor star up. As we can see, this happens automatically here, so the ejector rod is pushed up, and so too the extractor is pushed up. But this is done automatically as opposed to the swing-out cylinder revolvers we've seen in the past where the ejector rod would be pushed in manually by the user. Instead, the firearm itself does the pressing in of the ejector, and this is what makes it complex. Because not only do we have to push in the ejector, but we also have to release it. As we can see here, eventually it comes to a point where the ejector is released and allowed to come back down to allow the extractor star to come back down. So as you might have saw before, it's this part here that acts upon the ejector rod. And this part consists of a disc shape with an arm that sticks out that is going to be what acts upon the ejector rod. So how this works is the disc only rotates a little bit until this tooth comes up against the frame. And when that tooth comes up against the frame, it stops moving and rotating with the top part of the frame. And when it stops rotating, this arm holds back on the ejector, pushing it in and upward. But eventually, this disc is pushed up as you can see, the disc itself has this slotted cut that allows it to move up and down. It's going to drift upward and eventually break its contact with the lower part of the frame. This allows the disc to spin back down when the spring of the ejector releases its tension. This allows the extractor to come back down and allow us to put in fresh cartridges. Now, what causes this to occur is a camming action with the top part of the frame. And I'm going to have to come out of the x-ray so that you can see this. So you can see the disc here. And right now, this tooth comes up against the lower part of the frame and stops the disc from moving. But eventually, the top part of the frame, as it comes around, is going to cam along this tooth that sticks out from the lower part of the frame. And eventually, that top part of the frame is going to start to push up on that tooth. And once the tooth is pushed up far enough, it'll break its contact with the lower part of the frame, allowing it to spin. And as we discussed before, it's the ejector spring that's going to cause the disc to spin around. Now, as the action starts to be closed, what keeps the disc rotating with the frame is this little spring-loaded arm here. Now, this is going to be kind of hard to see, and I'm going to have to show you from a couple different angles and through a couple different versions of the X-ray. So right now, the spring-loaded arm is right up against the top part of this frame, which you just may be able to make out its interaction. And this is what allows it to rotate along with the top of the frame as the action is closed. So if we come back into the X-ray here, and we just take a look at what this spring-loaded arm looks like before the action is fully opened, it's actually sticking out a little bit, as you can see. So again, if we come out of the X-ray, you can see it sticks out quite a bit there. As the disc spins back around, though, it's going to be pushed in, and this arm is going to cam along its contact with the frame. So again, I'm going to come out here so you can see that. So as the disc spins, that arm's starting to get pressed in because it's sliding along the top of the frame here and getting pressed in. And then when the frame starts to go back closed, it's this squeeze in between this arm and the frame that gets the disc to spin back around so that it can fall back in place. And then once the tooth goes beyond the lower frame here, that arm is going to push out, bringing the tooth back down. So you can see the arm coming out just as the tooth comes down, and then the disc lowers down into its lowermost position so that when we open the action again, that tooth will catch the lower part of the frame. So just to show a little bit lower in the X-ray, you can see this is the arm, and here's the spring that acts upon it within the disc. Considering the main strength of a top break revolver, a potentially rapid reloading process, you may be wondering why there aren't any examples of a modern top break design. The reason is because of the main limitation of a top break revolver, its ability to handle higher pressure ammunition. Unlike a solid frame revolver like the Smith & Wesson example we looked at earlier, where the pressure can be spread throughout the frame, a top break revolver focuses most of the pressure at a single point, the latch. This is an issue that most break-action firearms have, and the strain over time on some break-action designs can eventually stretch the latch to the point of needing repair or replacement before the firearm will operate properly. The weakness of the strength of the action also limits how much pressure the revolver can handle, which is why during its earliest implementations it was more popular, as initially revolvers were designed to fire black powder cartridges, which produce a lot less pressure than later smokeless powder ammunition. Those firearms that use smokeless powder cartridges still were limited to relatively low-pressure rounds, and even reproductions of older designs using modern metals such as Uberti Smith & Wesson top-break reproductions are chambered for lower-pressure ammunition such as .45 Colt or .38 Special rather than .357 Magnum, for example. And the last example we're going to take a look at in this video is the Chiappa Rhino. And the main difference between this example and all of the other examples we looked at so far is the placement of the barrel, which is in line with the lower chamber on the cylinder rather than up top here on the upper chamber like every other example we've looked at so far. And the reason for this I'm not going to get into in the course of this video, but this one change has added a little bit of more complexity in the Chiappa than in other revolver designs, but a lot of that complexity is the fact that the Chiappa design attempts to keep a lot of the standard single action, double action functionality that you would expect out of a revolver in this different design, and that has added some complexity. And you might look here and see just a jumbled mess of parts and think that this is just a very much more complex design than we've seen so far. But if you've gone through this video and my previous video covering how revolvers work, there really isn't all that much different here than a lot of the other revolver designs. You just have to go through it and see what all the different parts do, and eventually you figure it out and realize it's pretty much the same thing we've seen so far. Let's go ahead and identify the main components. We have the cylinder with the locking notches cut into the side. At the back of the cylinder are the ratchet teeth, which are a little unusually shaped on the Chiappa, being more rounded pegs, but they function more or less the same way as we've seen before. Down here we have the cylinder stop, which is right next to the trigger. And over here we find the hand. Now the attachment point of the hand looks a little bit different than we've seen in the past. Well, that's because of the trigger in this part, which I don't really know the name of. But if you were to combine these two parts, in the past with our other examples, the functionality of these two parts would have been all one part, just the trigger. But now they've been separated into two parts attached by this link. Now, the importance of this link we'll go over a little bit later in the discussion of this model. If you consider these three parts to function all together as one, you'll see that their overall functionality is the same as the one part of the trigger that we saw in our previous examples. So with that in mind, we can consider the hand to actually be attached to the trigger like in our previous examples, because overall these three parts do function together as the trigger mechanism. With that being said, let's take a look at what happens when we cock the hammer back. So as the hammer travels backward, and this is the hammer back here, it's going to come underneath the trigger assembly and hook underneath it, just like we've seen in a lot of our other examples, causing the trigger assembly to pivot upwards on this end. And as it pivots upward, it's going to drive the hand upward. Now, as we've seen with a couple other examples, the timing of this animation is pretty poor, as we see the hand is not really even barely making any contact with the peg before the cylinder starts revolving. The hand would actually come up and contact the peg, roll along the rounded outer surface of the peg, rotating the cylinder along. The timing of this is very poor. More or less, the cylinder would not be rotating now. It would start rotating once the hand got to about there, and then we would have that rotation. So just poor timing here. You also see the hand interacting with another part here. This is pretty much the cocking indicator here. So what happens is the pin comes up, pushes in up on this pin, which is spring-loaded. And this is just to let the user know that the hammer is cocked back, because the cocking lever here, which looks like the top end of a traditional hammer, it's not actually the hammer itself. It's only partially connected to the hammer or interacts with the hammer. And when the cocking lever is done being activated, it will come back forward under its own return spring. And this pin here sticks out to let the operator of the revolver know that the hammer is cocked back or in the cocked back position. So that's what this is all about. And that's why the hand is doing that, because usually speaking, when you're cocking back the hammer, you're going to be bringing the hand up. So they're just utilizing that upward motion to activate this pin. Now, an interesting side effect of this is when you pull the trigger in double action mode, the pin will come up just the same as it does here, because the hand will still contact it all the same. It just will drop right back down as soon as the hammer comes forward. So let's go ahead and take a look at what happens to the cylinder stop as the hammer is cocked back. So just like with the Smith & Wesson model we looked at earlier in this video, the trigger assembly here, as it pivots up on this end, it's going to pivot down on this end due to its attachment point with the frame here. So it's going to pivot along this axis point, pivoting up here, pivoting down here. And as it pivots down, it's going to pull down on this end of the cylinder stop, which in turn pivots along its attachment point here through the frame. So as it pivots down, it's going to fall out of the locking notch, allowing the cylinder to rotate. But eventually, this end of the trigger assembly is going to slide past as it pivots and off this ledge on the cylinder stop. Once that occurs, the return spring here of the cylinder stop will force the cylinder stop back up and eventually into the locking notch. This is not lined up at all, I'm noticing. All right, well, that's not lined up properly, but it should be. So this is yet another error in the animation. As a matter of fact, I can even tell, look at the firing pin. It's not lined up with the primer at all. So this is an example of what you wouldn't want to see in a revolver, because the chamber, as you can see here, maybe actually, there we go. The chamber is out of line with the barrel. So this is poor functionality in a revolver. This is exactly what you wouldn't want to see. Let's go ahead and take a look at the reset of the hand and the cylinder stop as the trigger is pulled and then released. So with the pulling of the trigger, the hammer is going to come forward. And just as we've seen in our other models, the hammer is not interacting with the hand or the cylinder stop at all. So it comes forward, strikes the firing pin. No real interaction between those parts. I'd actually like to come in here and see as the firing pin strikes the cartridge case rather than the primer here in the animation. But yet, magically, we have an indent on the center of the primer. I don't know what did that, but okay. And as we go through here, we're going to have the release of the trigger, and as the trigger is being released, its return spring is all the way over here. So we have this lever here, and what's going to happen with this lever is the spring is going to act upon it and push it this way. And as it's pushed this way, it's going to pivot down on this end. So as it pivots down, it's going to pull down on the hand. So you see this lever is hooked by the hand here. So as it pulls down on the hand is actually going to drive down on the trigger assembly here. And as the hand comes down, what's going to happen is, and again, this animation is pretty poor here, but what would happen in real life is that the slope surface here would contact this rounded surface, causing the hand to skip over top. I guess it does show that a little bit. And then because of the angled surface here and the pivoting of the lever arm, we're going to have the hand be driven back underneath, which we don't really see happen here, the next ratchet tooth in line, ready to go. And as that occurs, just like with the Smith & Wesson, we can see, and I'll go out in the x-ray just so we can see it a little bit better. You can see an elliptical cut here in the cylinder stop. So what's going to happen is, as the trigger assembly comes up, it's going to push inward on the cylinder stop, allowing the trigger assembly to come beyond this ledge here and over top it so that it can pull down on the cylinder stop yet again. Now that the link here is clearly visible, I might as well explain what it does beyond attach the two parts of the trigger assembly together. And to do so, I've actually brought the animation back before the trigger's been pulled in. So as the trigger's pulled in, you'll see that the link pivots up along with the trigger and comes underneath the cylinder stop and into contact with the cylinder stop. Now what this does is it prevents the cylinder stop from being able to pivot downwards while the trigger is held in. The reason for this is to overcome a common flaw in most revolver designs. If you remember back to all of the examples I've covered in this video series, all of them depended upon one thing to keep the cylinder stop held up into the locking notch, locking the cylinder in place, and that's the tension of a spring. You can test this yourself if you own a swing-out cylinder style revolver. With the cylinder held out of the frame, press your finger on the top of the cylinder stop. You will find that it will push downward under the press of your finger. Ordinarily, this is not an issue, as the force of a full-strength spring is all you need to bring the cylinder stop up into the locking notches, and the cylinder stop is there mostly to resist horizontal movement that could potentially rotate the cylinder rather than vertical movement. A possible issue occurs if the spring has been weakened over time due to the use and wear. With a weaker spring, less energy is being applied to force the cylinder stop upwards, and a sharp jolt, such as during recoil, especially in harder recoiling revolvers shooting powerful loads, can counteract the force holding the cylinder stop in place, potentially allowing the cylinder to freely rotate during the firing of the revolver. To counteract this, the Chiappa Rhino uses the link to hold the cylinder stop in place while the trigger is being held in, the time that recoil is most likely to occur. Well, that wraps up this video covering how revolvers work. Revolvers are commonly touted as one of the most reliable and dependable repeating handguns. They do not have the same issues that an auto-loading handgun can potentially have because of their reliance on entirely mechanical function, rather than utilizing the energy produced by the combustion of the propellant in the ammunition. But that reliance on mechanical function can be an issue unto itself. Worn out springs, parts breakages, and objects getting stuck in the mechanism preventing it from operating properly can all potentially bring the function of a revolver to a grinding halt. And just like a fine Swiss watch, the best mechanical devices can be quite expensive. There are also other advantages and disadvantages to revolvers that are not related to their mechanical function, but as the focus of this video series has thus far solely been on the mechanical function of revolvers, that is a topic for another time. I hope you have enjoyed the video. This is Mouse Gunner, signing out.